In this video, we are going to demonstrate how arsenic in Bangladesh groundwater gets mobilized, how it's transported, and also what we can do about the problem. We are going to use the sand tank that you see in this image to illustrate the processes, and if you'd like to know more about how it works and how groundwater moves in Bangladesh, watch our other video about groundwater in Bangladesh. So this is what the situation looks like in areas of Bangladesh that are affected by elevated arsenic levels. We have a shallow aquifer on top and a deep aquifer at the bottom, and in this case they are separated by a protective clay layer. This is not always the case. Sometimes these two aquifers are connected. The red dye in the sand tank is visualizing the arsenic in the aquifer. As you can see, there is some variability in arsenic concentrations in the subsurface. Some wells will yield water with high concentrations of arsenic. Other wells have low concentrations. In Bangladesh, we often have areas where most wells have consistently high or low concentrations, and others where low and high arsenic wells are right next to each other. So what are the sources of arsenic in the subsurface? Arsenic in Bangladesh sediment has a natural source. It is transported by the big rivers in the area from the Himalayas. Organic matter is likely responsible for the release of arsenic from the sediment into the groundwater. Organic matter can come from the sediments, or it might be released by human activities at the surface and then transported into the aquifer. The jury is still out in terms of what sources are most important. In order to demonstrate that arsenic is released from the sediment to the groundwater, we will do a push-pull experiment. This experiment has two phases, a push and a pull phase. In the push phase, we add clear water into the shallow well that is now high in arsenic. By putting low arsenic water into the well, we displace the high arsenic contaminated water. Then we let the clear water sit in the aquifer for a few days and then observe what happens. After some time, the arsenic will be released from the sediment back into the water. In the pull phase of the experiment, we pump water out of the same aquifer, and we see the water in the syringe is red again, indicating that the well is high in arsenic. This experiment shows that arsenic is locally released from the sediment into the well water. When we look at arsenic concentrations as a function of depth, we see that shallow aquifers have high concentrations and deep aquifers have lower concentrations of arsenic. This is the case in most aquifers in Bangladesh. We have a peak in arsenic concentrations at a depth of about 50 to 60 meters. Several hundred meters in depth, the arsenic concentrations tend to be lower. This is primarily due to the fact that the shallow aquifers are geologically younger and still contain arsenic that can be mobilized, while the deeper aquifers have been depleted by thousands of years of groundwater flow through them. Because deep aquifers have lower concentrations of arsenic, people can obtain their drinking water from deep wells. This provides a solution for the arsenic contamination crisis in Bangladesh, especially in places where the deep aquifer is protected by a clay layer. In such places, the clay layer provides a barrier for any shallow contaminated water that might otherwise make its way into the deeper aquifer. Note that currently the water level, or hydraulic head, is higher in the deeper aquifer, and as a result natural water movement can occur only from the deep aquifer to the shallow aquifer. When we pump water from the shallow aquifer, we see that the water level in the shallow aquifer drops, whereas the water level in the deep aquifer does not change. When we pump water from the deep well, we see that the water in the shallow aquifer is not affected. This means that the two aquifers are well separated. However, increased pumping of deep wells causes the hydraulic head in the deep aquifer to decrease and become lower than the level in the shallow aquifer. As a consequence, there is the potential that shallow contaminated groundwater will infiltrate the deep aquifer. In the absence of a protective clay layer, high-capacity deep water well pumping can bring contaminated shallow water to the deep aquifer. In order to avoid deep well contamination, we should pump deep wells in a responsible and sustainable manner. Another problem is the potential that well casings break and allow for flow of groundwater from the shallow to the deep aquifer. One solution to the problem of vertical leakage is to pump water from both wells at the same time. We can use the shallow aquifer water for irrigation, where the water quality is not so essential, and use uncontaminated deep aquifer water for drinking water purposes. By pumping both wells simultaneously, the shallow aquifer at a higher rate than the deep aquifer, we will maintain the difference in water levels between the deep and the shallow aquifers. Therefore, the deep aquifer hydraulic head will remain higher than the shallow well levels, and we will eliminate the potential for shallow water to flow down and contaminate the deeper aquifer. In the presence of a protective clay layer, this is a sustainable pumping scenario in Bangladesh, as long as the negative effects of high arsenic water on food quality are limited. If there is no protective clay layer between the two aquifers, the contamination can move rapidly between two wells. If we focus on these two wells, we can see that one is high in arsenic and the other one is low, due to the spatial variability of arsenic concentrations in the subsurface. If we pump water from this well, we can see that it is currently low in arsenic, as demonstrated by the clear water in the syringe. If we pump a lot of water from this well in the absence of a clay layer, we'll pull the arsenic contamination from nearby. As you can see, the water in the well quickly becomes contaminated. Ultimately, we can contaminate a well that was originally arsenic-free. Another phenomenon that we see in the sand tank in the nature as well is that a lot of the arsenic ends up in the river. Since rivers tend to be the discharge area of an aquifer system, a lot of arsenic tends to flow towards the rivers. In the sand tank, the rivers turn red, which implies that arsenic levels are very high. In nature, however, this is not necessarily the case, because arsenic reacts with the oxygen in the atmosphere and a lot of it precipitates out. Arsenic levels are therefore high in the river sediments and not in the water itself. Arsenic in Bangladesh does not stay in the dissolved phase for very long if oxygen is present. Arsenic is not the only problem in Bangladesh that relates to drinking water. There is also a contamination related to the spreading of pathogens. Bangladesh doesn't have a sanitation system. There are no sewers that drain bathrooms. Latrines simply drain on the surface. Animal and human waste runs into the nearest depression, which is usually a pond nearby. As we learned earlier, ponds are connected to aquifers, so water that is in the pond penetrates the aquifer system. This can potentially contaminate the aquifer with coliform and other bacteria. We can simulate this process by using blue dye water that represents pond water that has been heavily contaminated with human waste. Observe how blue water from the pond enters the subsurface and spreads within the aquifer. Consider a pumping well nearby. When we pump a lot of water from this high arsenic well, we see that some of the blue dye makes its way into the well. The well water in the syringe becomes a mixture of red and blue. This is an indicator that the water in the well is now contaminated with arsenic as well as with pathogens. As a result, this water will be very unhealthy to drink. The points I wanted to make with these demonstrations are the following. Arsenic in Bangladesh is in the sediments naturally. It gets mobilized with groundwater moving by the sediments, and it's very spotty typically in the shallow aquifer. There are places with high and places with low arsenic concentrations, and by pumping on these wells we can mobilize the arsenic and move it to a different location and eventually contaminate a shallow groundwater well. The deeper aquifer in Bangladesh tends to be low in arsenic, so it's an obvious solution to the problem to pump from the deeper aquifer, which is currently low. However, there's the danger that by pumping very hard in the deeper aquifer, we are pulling the arsenic down from the shallow aquifer into the deeper aquifer. And we can avoid that to some extent by pumping both aquifers at the same time, and therefore providing safe drinking water for long times in the future.